Sheathed in titanium, the X-3 Stiletto introduces a new chapter in aircraft design. Later, the Convair Sea Dart becomes the first seaplane to go faster than the speed of sound. These and other X-planes test the bounds of aviation, taking flight design into a new era. Not all of the X-planes have been spectacular successes. In fact, many never broke any barriers or records. This is the sleek Douglas X-3 Stiletto, flown in the early 1950s. The Stiletto was built to explore high-speed aerodynamics at 2 times the speed of sound, but because of power plant deficiencies, it barely entered supersonic flight. For high-speed research, it was arguably a failure. But the X-3 did contribute to our overall understanding of aerodynamics. Test pilot Scott Crossfield.
You do research to find answers, and really you don't necessarily do it to get those answers to come out the way you want. You just want to know what nature's trying to tell you with its physics.
X is for experimental. And many experimental aircraft have explored new shapes and concepts that didn't quite succeed, but nevertheless taught us much. During World War II, German designers developed the rocket-powered Me-163 Komet. It had swept-back wings and no horizontal tail. This tailless configuration had advantages at very high speeds. The Komet was the fastest aircraft of World War II.
Every generation of aerodynamicists since the Wright brothers has tried to make a tailless airplane. The drive is that they could be very efficient if you could get the stability and handling qualities.
The DH-108 Swallow was built by the British de Havilland Company after the war. Designed to explore the tailless configuration, the Swallow project suffered tragic losses traced back to control and stability problems at high speeds. In fact, 3 Swallows were lost, putting a black mark against the tailless design. Another tailless research aircraft was the Armstrong-Whitworth AW-52, which first flew in November 1947. Many designers of the time felt certain that this low-drag shape would dominate the future, and that any unsolved problems could be overcome. An even purer form of tailless aircraft was the Northrop YB-49 Flying Wing. Jack Northrop pursued the idea for many years. In 1946, Northrop was given a contract to build a tailless X-plane, the X-4 Bantam. The tiny X-4 was one of the Air Force's smallest aircraft. 2 Westinghouse turbojet engines were buried in the wings. Any space left was packed with fuel and research instrumentation, leaving little room for the pilot. Huge split flaps served both as landing flaps and dive brakes. The wings were lightweight magnesium, but the rest of the aircraft used more conventional materials that tended to suffer during high-speed maneuvers. Pete Everest flew for the Air Force.
We had a lot of trouble with fuel leaks and this sort of thing, and you pull G's away, you'd break some of the seals and cause fuel leaks, and they have to start filling up, put gook in to try to fill up the leaks. And I think when they finally finished, when NASA finished flying X-4, I think it was almost filled up with gook instead of, he couldn't get much gas in it.
The first of only 2 X-4s built had its maiden flight on December 16, 1948, flown by Northrop's Charles Tucker. It was the start of a test program of over 100 flights, spanning 5 years. The X-4 demonstrated good stability and control until it entered the higher speed ranges. There, pilots noted strange oscillations likened to a roller coaster ride. The X-4 had shown that to fly at these higher speeds, a tail was needed.
There's an old saw, you can't give a fighter pilot and an airplane enough tail, you know. And we needed the tail volume. We found out that just now all airplanes are pretty much shaped that way.
In 1953, the X-4 flights were finally halted by recurring fuel leaks. There were no major accidents, and both X-4s survive today. In the late 1980s, the Western Museum of Flight organized the restoration of one of the X-4s. Many Northrop employees helped out on the project. The restored X-plane was bound for permanent display at the Air Force Museum in Dayton, Ohio. The first man to fly the X-4, Charles Tucker, remembers how the X-4 seemed tailor-made for him.
It was a tiny airplane and I was a little fellow. They needed somebody about my size to fit, and apparently I had the qualifications. This was one of the first small airplanes to use the all-hydraulic control system, which you have to go fast these days. The human pilot can't handle the control forces.
It was a research success because it demonstrated what was at that time unknown about what the aerodynamics of a tailless airplane was at transonic speeds, and we learned what it was, and so as a result it was a success in that sense, but it told us that we ought to try other avenues to get good transonic airplanes, and we did.
The X-4 taught us that we'd have to find other ways to gain the benefits of the tailless configuration, and we have. Despite political controversy, the Northrop B-2 is a successful tailless aircraft. It overcomes the configuration's problems with synthetic stability provided by computers. This is the Convair XF-92A Dart, built to research the flying characteristics of the Delta wing. Test pilot Scott Crossfield flew the Dart on many occasions, including its final flight.
That was our first Delta, and really it was the one that filled out initially the data bank that's been used in France and Sweden and everywhere else in the world where they've leaned towards the Delta configuration, and it contributed a tremendous amount negatively that made us do positive things to correct the problems.
At the closing stages of World War II, the designer of the Me-163 Komet, Alexander Lippisch, explored other designs, testing a series of triangular wing shapes. After the war, Lippisch brought his designs to the U.S. and proved the Delta shape had many desirable high-speed qualities. The Convair company showed great interest in these studies and started their own test program. The direct descendant of Lippisch's work was the XF-92A Dart. Convair had given the little jet very thin wings to aid high-speed performance. The tail and wings swept back at an angle of 60 degrees. On September 18, 1948, the XF-92 chalked up the first flight of a true Delta wing aircraft. Many flights were to follow over the next 5 years. Convair, the Air Force, and the National Advisory Committee on Aeronautics, NACA, all put the Dart through its paces in the skies over Edwards Air Force Base. The Delta Promise was a faster aircraft for less power because of the clean aerodynamic shape, a more maneuverable aircraft that performed better at supersonic speeds. The negatives were poor performance at low speeds, a strange tendency to pitch up during maneuvering, high-speed landings, and long takeoffs. Once in the air, the XF-92 required good piloting skills to push into the higher speed ranges. The violent pitching up happened during turns and could be quite a surprise to the uninitiated. Still, it seemed the Delta could be the shape of the future. The XF-92A was retired in October 1953. The 5-year research program had demonstrated many problems with the Delta, but it had also given designers a chance to solve them.
That was a very, very productive airplane, and we only really did a 25-hour research flight on it, a research program on it. And I flew most of that, and we learned an awful lot from the 92. I really what not to do, but it served its purpose in research.
Other Delta aircraft followed the XF-92, benefiting from its discoveries. This is the Convair Sea Dart. It was an experimental Delta wing fighter seaplane. First flown in April 1953, it took off from the water on retractable hydroskis. The Sea Dart was the first seaplane to exceed the speed of sound. Another Convair-built Delta wing experiment was the XFY-1 Pogo. The Delta shape seemed perfect for an aircraft designed to sit on its tail for a vertical takeoff. Powered by a turboprop, the Pogo made its first complete vertical takeoff and landing in November 1954.
We learned many ways with fences and devices to get the advantage of the swept wing, which is very good advantage transonically and low drag at low angles of attack supersonically. So the 92, even though it was not a good flying airplane, had very few good characteristics, taught us a lot of ways to develop that family, which became the 102, the 106, and a lot of the Swedish and French airplanes.
The F-102 Delta Dagger was the first in a long line of operational Delta aircraft from Convair. The XF-92 explored various ways to solve the violent pitch-up problem of the F-102. After other substantial redesign work, the F-102 was to go on to a distinguished combat career. Throughout its deployment in Southeast Asia, the 102 established a remarkable safety record. Only 15 aircraft were lost over a 7-year period. Even more recent developments have drawn on the XF-92A's Delta legacy.
I think probably the 92 started the database that became the Space Shuttle, for instance. It's essentially a Delta wing with some modifications.
As the shuttle's Delta shape glides towards a safe landing, one can understand the need for research aircraft to make the mistakes and forge the way for others to follow. Much was anticipated when the sleek X-3 Stiletto was first presented to the public in 1951. Test pilot Pete Everest flew the X-3 for the Air Force.
The X-3 was originally built to be the first turbo-powered airplane to go supersonic. Unfortunately, the engine that was supposed to go in it grew too big and wouldn't fit, the engines, I should say. So they had to put a lower thrust-rated engine in the little bird, which detracted from it drastically.
By the time it first flew in late 1952, it was apparent the X-3 would be disappointing. Originally designed to investigate sustained flight at Mach 2, Westinghouse's inability to provide the specified size and power-rated engines seemed a fatal stroke. But the decision was made to carry on with the X-3. J. Miller, aviation historian.
What it became, in effect, was number one, a hangar queen, and number two, believe it or not, a structural and materials test bed more than an actual research aircraft.
Beyond performance problems, it proved a true pioneer. This hatch in the X-3's underside was quite novel.
The cockpit was enclosed from the top, and you got on the cockpit seat from the bottom, and then you had a little elevator that brought you back up into the cockpit. And then they closed the door underneath you. And of course, that was the first airplane with downward ejection.
This escape system was an attempt to avoid the high-set tail during a bailout. The designers had at one time included ideas of a jettisonable nose section. Evacuation on the ground could be through the removable cockpit side windows. The razor-thin wings, machined out of a single block of aluminum, spanned only 22 feet. The long nose contained 1,200 pounds of instrumentation. One of the X-3's most significant technological contributions was the use of titanium. It was light and strong with a high resistance to heat, but it had always proved difficult to work with. Douglas pioneered new practical ways of fabrication and construction with titanium that are still used today. A bonus of the X-3 program was its contribution to the development of new standards for aircraft tires.
We had to take off from the leg bed because it had such a long takeoff run. We had to strip all the tread off the tires because it would throw tread. And I think it lifted off at about 230 knots and took a long time to climb at altitude.
When it finally made it into the air, the X-3 must have been a great disappointment to the pilots. A great body, but what a shame about the engine.
Because it was so underpowered, it probably didn't provide too much data. Probably wasn't worth all the cost and the money used to get it airborne after it lost its larger engines.
But aesthetically, the X-3 stirred the imagination for what it might have been.
It looked pretty, yeah. It looked like a dagger ready to go.
The X-3 flew only 50 times. Its most important flight took place on October 27, 1954. Test pilot Joe Walker experienced an abrupt loss of control, and his attempt to correct it had the reverse effect. However, he finally did regain control. Bravely, he tried inducing the problem, and again found the same loss of control. Walker had by accident stumbled across the phenomenon called inertia coupling. The occurrence of this on a test plane packed full of precision recording instruments was a godsend. Joe Walker didn't try his luck a third time. This flight had inadvertently unlocked the door to the mystery that had claimed several new F-100 Super Sabres. To fly aircraft at supersonic speeds safely, this problem needed to be solved. The data from this flight made the once redundant X-3 invaluable, and inertia coupling less of a mystery.
Later on, I think an additional 20 flights were flown wherein he specifically went up in the X-3 and explored this phenomena. And from that data that was gathered during the course of these 20 additional flights, aerodynamicists began to get a grip on what the problem was.
Only one X-3 was built. It survived its flight test program. and was retired after its final flight on May 23, 1956. The Douglas X-3 Stiletto is now on display at the U.S. Air Force Museum in Ohio. Although initially a disappointment, in the end it taught many vital lessons. All X-planes are by name experimental, their ultimate worth being that of a signpost, pointing to a better way. Inspired by a captured German aircraft of the Second World War, the X-5 pioneers the in-flight adjustable wing. Proving the concept works, the X-5 sets the stage for future designs. And it's with the F-111 and the F-14 Tomcat that the swing wing finally comes of age. The Bell X-5 flew during the early 50s, doing at the time what no other aircraft could. The X-5 could transform its shape from a straight wing to a sleek swept-wing aircraft in mid-flight. But why would an aircraft need to perform such a metamorphosis? A swept-wing design like this XF-92 experimental aircraft performs well at high transonic and supersonic speeds, but at lower speeds it suffers reduced lift. So takeoff and landing speeds must be very high, making them difficult and dangerous. Although not efficient at high speeds, a straight wing has an advantage at lower speeds. It produces more lift, enabling the aircraft to take off and land at a slower, safer pace. During the final months of World War II, the Allies swept across Europe discovering exciting new technology. Jet aircraft, data, plans, and personnel were taken back to the U.S. These were the fruits of war. Before capture, this Messerschmitt P-1101 with its ground-adjustable wings was used to test different wing sweep angles. In 1948, Bell Aircraft began development of a variable swept-wing aircraft with the P-1101 as the starting point. J. Miller, aviation historian.
With the P-1101, because it was a ground-adjustable system, there were essential elements missing. An example is that ground-adjustable variable sweep wings require no mechanical system in order to articulate those wings while the airplane is flying. So first and foremost, you have a weight element. This, in turn, is one of the things that helped dictate the size of the X-5. Again, aerodynamically, it was based on the P-1101, but those are the only similarities between the two airplanes.
Bell technicians put a great deal into developing the X-5's wing. It would delay the project for over a year. One complication was the fairing around the wing roots. Another problem, as the wings moved, they changed the aircraft's center of gravity.
There were three essential points with the X-5's design. Number one, the airplane was designed to accommodate a center of gravity changes as the wings swept forward and backward. Number two, they were designed to accommodate what are called center of pressure shifts, which are the end product really of airspeed and altitude. And then number three, the most difficult and complex part of all this was how to articulate these wings mechanically.
By early 1951, the wing sweep system was installed and the X-5 was complete, ready to fly like no other aircraft had flown, able to reap the benefits of straight and swept wings. X-5 test pilot Scott Crossview.
The variable sweep wing is ideal because it's very fundamental that you want the straight high aspect ratio wing for the low speed end of the scale, and you want a highly swept wing for the high speed end of the scale. And of course, that's as, hey, you can't afford a low-speed airplane, a high-speed airplane, and so you swing the wings.
To counter shift in the center of gravity during sweepback, the wing root slid forward as the wing tip moved backward. It could sweep from 20 to 60 degrees in about 20 seconds. Disc brakes then locked the wings at the desired angle. The whole system was driven by electric motors, and although very complex, never really proved troublesome. The wings were amazing pieces of engineering, giving the X-5 many advantages, but at a cost. Pete Everest flew the X-5 for the Air Force.
Putting movable wings on an airplane is very expensive weight-wise. And obviously sophisticates the airplane and makes it hard to maintain.
An ejection seat added more weight, but was now the standard on all planned X-planes. Tests were carried out at Bell in early 1951. At around the same time, with the X-5 tied down on the Bell test ramp, the first engine run-ups began. For the test, the nose intake was screened to prevent ingestion of particles. These early runs showed an engine cooling problem, so the standard fire precautions were adhered to. The Bell-modified Allison J-35 turbojet could produce 4,900 pounds of thrust. After a series of static runs, structural tests, flight control tests, and more, the X-5 was ready for its first taxi trials. These were initiated in April 1951 at Bell's Wheatfield plant by test pilot Gene "Skip" Ziegler. The landing gear of the X-5 had been a major challenge. The placement of the engine, although efficient and easy to maintain, had complicated its design. The high-set canopy provided good visibility, and the cockpit, unlike most X-planes, was quite roomy. With the basic tests completed, the X-5 was to be sent to Edwards Air Force Base to begin its flight program. With wings and tail removed, the X-5 was carefully packed into a Fairchild C-119 flying boxcar for the long haul to Edwards. On June 9, 1951, the first X-5, packed snugly in the C-119's hold, flew out of the Bell plant in upstate New York, bound for Edwards, high in the Mojave Desert. The X-5's arrival marked the third X-plane to make Edwards its home. The Bell support team set about the reassembly process. Well crafted, it was an easy-to-assemble aircraft, much simpler than the early rocket-powered X-planes. Scott Crossfield recalls.
It was a good, useful airplane. Being a jet airplane and not very complicated, it was easy to get flying. A lot of the research airplanes were very difficult to get in the air because they were kind of handmade.
By the morning of June 20th, 1951, assembly, preliminary ground tests, and system checks had been completed. The X-5 was now ready for its first flight. The initial flights by Bell were to demonstrate to the Air Force and the National Advisory Committee on Aeronautics that the aircraft could fulfill the basic requirements of the contract. The perfect place to do that was at Edwards. The Edwards facility had grown since the early post-war days, and it was well on its way to becoming the premier flight research center in the U.S. Its attraction was the all-year-round flying weather, the isolation, and of course the perfectly flat 65 square mile Rogers Dry Lake, the largest natural airstrip in the world. Chief pilot of Bell's flight research program, Gene Ziegler, would complete the evaluation flights. The X-5's high-speed takeoff run stretched across the vast dry lake. After 3 years of development, the X-5 was finally up and away. Its first flights were at low speed, and the wing sweep system wasn't operated. In the sky, the X-5 displayed characteristics that wouldn't exactly endear it to pilots.
It was a lousy flying airplane because it was a compromise of design where the thrust axis, the drag axis, and the principal axis weren't coincident, so anything you did gave it a lot of spooky dynamic motions, and we learned to fly around that.
The first in-flight wing sweep occurred during its fifth flight on July 27, 1951. It was only a partial sweep, but on the ninth flight, a full sweep was successfully executed. The X-5 was now the first aircraft to transform itself in flight into a completely different kind of plane. This central feature was a great bonus.
We couldn't afford to build an airplane with 10, 15, 20, 30 degrees of sweep, so we had a little cruder way of doing that by sweeping it in flight and getting comparative data over the entire sweep range up to 60 degrees.
During the X-5's pre-production, many doubted the worth of its unique abilities. There were many aircraft that had 20, 40, and 60-degree wing sweeps, and they'd already furnished mountains of data. So what could the X-5 provide that was new? Unlike conventional aircraft, the X-5 could be redesigned in mid-air. With subtle changes, aeronautical engineers could explore the optimum wing sweep angles for many different kinds of aircraft of the future. The beginning of the 50s saw unprecedented growth at Edwards. The Korean War was stimulating the expansion of the facility, which now boasted a population of around 5,000. Projects like the X-5 were an important part of a growing database demonstrating how to build better, safer, and more efficient aircraft. These were the golden years of flight research. Test pilots and aeronautical engineers looked on this barren, desolate expanse as fertile fields of new ideas and knowledge. Here was a group of brilliant technologists and courageous pilots, literally in the middle of nowhere, piecing together the shapes of aircraft to come. The National Advisory Committee on Aeronautics, or NACA, was the forerunner of today's NASA. Each X-plane was packed with NACA test equipment, and findings were disseminated to all fields of aviation research and development. The parched winds that blew across Rogers Dry Lake signaled the blustery winds of change. Air Force personnel only flew the X-5  8 times. The majority of the program was flown by NACA pilots. What was learned would benefit the military years later. But Bell hoped for more immediate results. They felt the unique X-5 deserved a place at the front line. This is the Bell Prime Mover, a motorized wheelbarrow. As the massive defense contracts dried up after the war, companies were forced to diversify. And 1946 saw one of the world's finest teams of aircraft engineers designing a wheelbarrow. Bell Aircraft was struggling to stay alive, and founder Larry Bell worked tirelessly to interest the defense agencies in initiating new production contracts. Bell's research and development on the helicopter eventually would pay off, but many other projects like the XP-77 were successful technologically, but finished up as dead ends. With aircraft like America's first jet, the P-59, Bell won fame for its advanced concepts. However, the P-59 only entered limited production. Other companies would win the big manufacturing contracts, benefiting from Bell's pioneering achievements. Bell hoped that the first supersonic aircraft, the X-1, could be developed into a high-speed interceptor. Designers struggled to include a conventional landing gear to make the idea more appealing. But the X-1 would only land a place in history. Behind all of these original aircraft was Bob Woods, Bell's maverick chief engineer, who in the 50s turned to the X-5 as the new hope.
In combination with the initial objectives of the P-1101 studies that were done in Germany, he became convinced that the X-5 in a production configuration would make a real good fighter, and one that offered, good low-speed handling characteristics as well as high performance. And as a result, he proposed an armed version of the X-5.
As far back as 1948, Woods had proposed several fighter versions of the X-5, which interested some high-ranking Air Force contacts. Apart from aircraft, the company produced a range of military hardware. A successful light fighter would contribute much to Bell's many production arms. But Wood's enthusiasm failed as the Air Force flew the X-5 and came across many problems. Overall, they found the X-5 too small to carry the required fuel and armaments. It would need major strengthening and aerodynamic redesign, a new ejection seat, and landing gear. The fuel tank that sat dangerously over the hot engine would have to be moved, and capacity doubled. In the end, they were talking about a whole new aircraft.
Obviously, the primary objective was to bring a contract to Bell and keep the company alive in this pretty tight post-war period. Fortunately or unfortunately, it depends on what side of the fence you stand on, the X-5 never got beyond the 2 prototype airplanes that were built.
But with its broad performance abilities, the X-5 did prove useful in another role.
The airplane was found to be reasonably dependable. It was reasonably easily maintained. And again, it was a docile airplane, relatively speaking, in a low-speed configuration. And because of the broad range or the span of its performance from low speed to relatively high speed, it made a pretty good chase airplane.
Overall, the little swing wing displayed fairly good flight characteristics. But the pilot had to beware of its one lethal trap.
The airplane did have a notoriously bad reputation, and when it came to spin characteristics, and in fact, it was an airplane that there were many warnings passed all the pilots: do not get into a spin in the X-5.
The 14th of October 1953 was the X-5's blackest day. Air Force Major Ray Popson was performing stall tests when the vicious design flaw reared its ugly head.
That airplane killed Popson. He got into a spin around 9,000 feet, and it took about 10,000 feet to get out of a spin in that airplane. He just never had an opportunity to get out.
And I was flying. I wasn't chasing him that day, but I was listening to him and told him how to get out of a spin, and it didn't work. We never know why.
The X-5's legacy was to lay dormant, but it was the seed of knowledge for a new kind of plane.
Overall, it proved that a variable sweep wing, jet-propelled, high-performance aircraft could be built.
And that plane was the General Dynamics F-111. The first prototype flew in 1964. It was the first operational variable geometry aircraft to fly. Although it experienced early problems, it went on to operate around the world and distinguish itself as a truly great combat aircraft. The swing wing's advantages have proved invaluable to the Navy. The premier ship-based fighter is the F-14 Tomcat. Its ability to fly such a broad flight profile dependent on variable swept wings. The Bell X-5 flew for only 5 years, the program ending on October 25, 1955. Although a flawed design, the little swing wing paved the way for others to follow.